as I mentioned before, I think it's very important to see theorems once in a while in calculus. And I'm not going to attempt to prove everything, and nor will I attempt to prove everything in some rigorous manner. However, I think it's important to see these, again, because it helps you learn how to figure out things in math, why things work as they do, and give you some insights. It also reinforces some ideas. So anyway, let's start with, I think, the easiest one. Now, remember, this is the definition of the derivative. Derivative of f of x of a function is the limit as h goes to 0, f of x plus h minus f of x over h. And again, that was that's the slope calculation at a point. And so if I want to take the derivative of a constant times a function, then I've got the limit as h goes to 0, the constant multiplying x. Think of this as a block, would be c f of x plus h minus c f of x over h. Now look at this, we can factor out c. So we can factor out the constant from here, and I'm just going to get the constant times the definition of the derivative. And so this is c times f prime of x. There you go. So probably the easiest theorem to see is the one that says that the derivative of a constant times a function is the constant times the derivative. Now, that only applies when this is a constant. I can't have an x here. You cannot factor an x out of a derivative and expect that to work. It just never will. So anyway, that's one. Now the other one, the derivative, and I'll use a short notation here, derivative of the sum of two functions, f of x plus g of x. I'll just write them as f plus g. That would be the limit as h goes to 0 of, well, what do we got here? We have f of x plus h plus g of x plus h. So that's this part right here, replacing x with x plus h minus the sum f of x plus g of x, and still divided by h. So what you have here is that these can be split up into two limits. So limit h goes to 0, and we have, well, you can see what's coming probably. So I took the f's out, and then I also have a separate limit. I can think of it as a separate limit by taking the g's out, g of x plus h plus minus g of x. The minus sign distributes across there over h. And look at that, very simple. So what we have is f prime plus g prime. Alright, so the derivative of a sum of functions is the sum of their derivatives. Okay, and if you put it minus here, that would be a minus there. You would just have to deal with the signs there. So anyway, I wanted you to see why that works. And combined together, that means that the derivative function, the derivative is an operator. It's not a function, but the derivative is an operator operating on functions. And I should say it's a linear operator. Okay, and linear operator, it's not going to mean a lot to you right now. Maybe later down the road, if you take some more math, you'll see that term come up. All right, so I'm going to erase this mess, and I'm going to tackle the big one, the derivative of x to the nth power. I want to show you. I can't prove the whole theorem right now, derivative of x to the n, but I'm going to get started on it. I'll show you parts of that theorem, and as we build up some more derivative rules, we'll be able to eventually prove the whole thing. So I'll erase this, and we'll go back to that one. So here's our theorem that we've been using. The derivative of x raised to the nth power is n times x to the n minus 1 when x is not 0. X is not equal to 0. Because, like we mentioned before, if x was equal to 0, in some cases, this would end up being division by 0. Okay. Anyway, it's kind of crazy. All right, how can we prove this? Well, all I can do is, at the moment, my proof is confined to when n is a natural number. A natural number is a counting number. N equals to, well, would it work? Well, n equals 0? Yeah, it would work for that also. N equals to, well, let's go 1, 2, 3, 4, and so on. I'll just stick to the natural counting numbers, 1, 2, 3, 4, and 5, and so on. If for n equals 0, I think you would just work it out directly and be very easy. Derivative of 0 is equal to 0. So I'll start with n equal to 1. Now, when these become fractions, it's more complicated. When they become negative numbers, it's more complicated. When they're irrational numbers, that's really complicated. So I'm just going to take these on as we develop the tools to prove it. But I love this. I love this proof because it gives me a chance to throw some out to you called the Binomial Theorem. And the Binomial Theorem says this. And you can look this up. It's possible that some of you have seen it. Sometimes it's taught in college algebra or pre-calculus. It says that if you take, I'm going to structure it this way. If you take a binomial, I'm going to write it as x plus h to the n power and expand it out. As long as these are positive whole numbers, positive integers. Then you're going to get x to the n plus n h x to the n minus 1 plus n times n minus 1 over 2 h squared plus times x to the n minus 2. And then it continues on, eventually comes down to h to the nth power. Okay. For a full version, you could Google it or look it up in some math books. You'll find the Binomial Theorem. And these coefficients end up being factorials. So if you've seen factorials, you could substitute there. Very often when you introduce the Binomial Theorem, you also introduce Pascal's triangle. So some of those might be some familiar terms for you. All right, so for example, if I add x plus h to the 4th power, I'll get x to the 4th plus 4hx cubed plus 6h squared, x squared plus 4h to the 3rd x plus h to the 4th. All right, so I'm kind of asking you to take my word for it. It comes from the Binomial Theorem. But the main thing is that the powers of x's are declining, and the powers of h are increasing. H to the 0, h to the 1st, h to the 2nd, h to the 3rd. And the part we're really worried about is, in our theorem, is going to be this part. Okay, this will make sense. So bear with me here. All right, so I'm going to erase the board. I'm going to show how this works. So I started off by plugging our function x to the n into the definition of derivative. So it becomes, this derivative is limit as h approaches 0, x plus h to the nth power minus x to the n. Everything is divided by h. All right, so it really comes directly from that. Now, here's where we need that binomial theorem. I need to expand this out, at least for a little bit. So I have the limit as h goes to 0, and on top we've got x to the n plus n h x to the n minus 1 plus other terms h squared times other terms and then minus x to the n, all divided by h. All right, so I did something rather unrigorous looking, okay, but I thought, well, let's cut to the chase on this. When you expand out x plus h to the nth power, suppose it's x plus h to the 7th power, you'll get x to the 7th plus 7h x to the 6th plus, I don't know, 21, I think, 21, maybe h squared x to the 5th power, and then you'll get maybe 35 h to the 4th x to the 3rd, something like that. Anyway, all the other terms you get when you expand this, after the first two terms, have at least an h squared in them. And so I'll just lump everything else together, just call it other terms, okay? You know, if you're, if you're in graduate school, don't try that, okay? You gotta be a little more rigorous than this. But it pretty much is what's happening here. All right, now look what happens. The x to the nth cancels. Very nice. That goes. And at that point, the h will divide into both these parts. H divides off there, canceling the h. And it cancels one h there, so I have h times other terms. So look what we have. We have the limit. You can probably see it, but I thought I would unclutter it here. And I've got n x to the n minus 1 plus h times other stuff. I'll just call it other. And as h goes to 0, we don't know what that's going to be, but 0 times it's going to be 0. So this part goes to 0. And now we're done. Only thing left standing is n times x to the n minus 1 equals nx to the n minus 1. All right. There you go. So that's the part 1 of the proof of this. And I want to prove the rest of it for other values of n. But like I said, we don't have the theorems yet. We don't have a theorem yet dealing with what if you're taking the derivative of a product of functions, or how about a quotient of functions, or a function raised to a power. Okay, so we have to develop those other theorems. And one thing I really want to impress upon you is that theorems are important. They lay the foundation for this subject, and also you can't go against those theorems. You can't just make up your own stuff and expect it to work. So, okay, well, we'll move on from here.